All right, so yesterday we were talking about AC, alternating current, and now let's take it up a notch because yesterday was too easy.
Yeah, that was too easy.
All right, we left off talking about RMS. What is RMS? That is right. It's like the average, but not. All right, so we were at 0.6, 0.7. Most instruments, meaning your volt ohm meter, VOM, measure in read in RMS. All right, so let's take a look at kind of what that means, something we're familiar with. So we'll say household voltage measures, we're going to call it 120 volts today. 120 volts. So what is the actual max voltage? What is the max voltage? So you remember the formulas we gave yesterday, unless you're watching it online, then who knows. So E max is what we're looking for. Max equals 1.414 times E effective. Remember, effective was the same thing as RMS. So that's the same thing as saying E max equals 1.414 times 120, which means that E max equals 169.68 thereabouts. So E max. So if we looked at it on an oscilloscope, then we would see it going up like that and then back down, and we would say, well, RMS is right about here at 0.707, so that's the RMS, what we're going to read on our meter, and that would read 120, and up here is the peak, which would be 169.68 volts. So, all right, so we're going to get that straight. So actual peak voltage would be 169.68. What is the peak to peak on that then? 169.68. 8 times 2 is 339.36 peak to peak. Peak to peak. We'll do one more. So if a certain peak voltage of 50, so peak of 56 volts, as indicated on the oscilloscope, what is E effective, or the RMS? What do you got?
39.5976.
How do we get that?
So 56 times 0.7071.
0.707. 7071 equals
39.59.
39.59. So E effective. So what is this? So E effective or RMS equals 39.59 volts. All right. Good. Everybody good with that?
What is after 339.36 for the peak to peak?
6.8.
No, after that, the total 339.36.
Peak to peak.
Thank you.
All right, so let's see. The last point was 7 in my notes. Now say I'm back to 6. So we'll call it 8. Make a note. 8. All right, switching gears a little bit now. So we've talked about RMS and peak to peak and how to read an oscilloscope. And we talked about what the waves, different kind of waves and all that stuff. So let's talk a little more about some of these circuits. So let's talk about an AC resistive circuit. And I believe I'm going to get to this in a little bit, but when you talk about AC circuits, you have R, C, and L circuits, or a combination. That's resistive, capacitive, and inductive. So it's a combination. So right now we're just talking about the R. So a resistive circuit. So this is a circuit that contains only resistors. Or in other words, no coils, no capacitors. Ohm's law, you've heard of this, probably. Oh, it's on YouTube. Ohm's law is applicable just like with a DC circuit. Actually, can you can't really say, yeah, direct current circuit. Yeah, I can't see. Can't say DC current. All right, I think I'm going to skip these examples because you know them by now.
You sure?
Or there's nothing I can do to teach them to you. So you either know them or I'm going to say the same thing and be like, I don't get it. What don't you get? Everything since August the...
Yeah, everything since the first day we got here.
Yeah.
Who's law? What's his law?
Who is that?
That's a suggestion, right?
Yeah.
Wait, this is 311?
Wait. Yeah, please, somebody, now it would have been great if you said, I still don't understand how this is going to help me be an air traffic controller. When did we start that? I don't get it. You know, it seems like, especially for him, because he's almost, halfway through his second semester. Okay, in a purely resistive circuit, meaning resistors, purely circuit, circuit, in a purely resistive circuit, volts and amps are in phase. And you remember what we talked about yesterday about that means that as the voltage goes up, the amps follow it. So it's kind of a lockstep. When one hits zero, the other hits zero. When the other one peaks, the other one peaks. So they are in phase. That's good. That's a good thing. We want that. They are in phase. Yeah, when I have all this stuff written, I'm afraid if I write it, then your hands will get crampy. If I don't write it, you'll be like, we didn't say that. So when voltage reverses, amps also reverse. Amps also reverse. In every step in time, that's it, time. Every step in time, volts are doing the same thing as amps. Volts are doing the same thing as amps, except at a different amplitude, meaning not the same. So volts would be higher than amps. Different amplitude. And D, the power, yeah.
I was just confirming when you said that volts and amps are in phase, they will always be in phase in a resistive circuit.
Always.
Okay.
It takes something else to knock them out of phase.
Okay, that's what I was.
So the power consumed by the circuit, by the circuit is the same as a DC circuit, which is power equals E RMS times I RMS. All right, I don't know if I want to do this, but I'm doing it anyway. Seems simple. Question. All right, solve this. We have a 110 volt supply in a parallel circuit. So we have R1 equals 10 ohms and R2 equals 10 ohms. So that would look like this now. So it's AC, it's parallel. What does it look like? Didn't know I didn't do that. Got the answers? I didn't bring my calculators. You have to help me out. What? So I have 110?
Yep.
1. Whoa,
Whoa.
that's crazy.
It's like on the law.
What's my total resistance?
5 and
5 amps. Current flow?
Hold on.
Ohms. Well, you're not going to learn anything if I'm going to do that kind of crap. Okay. It's because I went up the line. All right. So, current flow. 22. 11 amps. 11 amps. There we go. Okay. What's the power?
2,420 watts.
2,420 watts sold. Okay, what is the peak value? What is the peak value of I? So that'd be I max equals 1.414
31.108.
times 22. So I max equals
31.108.
1. We'll just go 31.1. Thank you for being exact. All right. Not hard, right? Everybody's up to speed? Okay. What number am I on?
9.
You speaking German or are you giving me a number?
So any value that they give you in a circuit like this, that when it comes to amps, current, or I guess amps or current, it's going to be an RMF
Unless otherwise stated. Or unless I meant to write it but didn't.
gotta know.
Then you just have to know it. It's just helpful if you know what I'm thinking. Okay. Got that? Resistive circuits. We're done. Moving on. So that was easy, wasn't it? Okay, now we're going to totally shift gears and talk about some cool stuff. So magnetic fields. All right. So up until now, because we've been talking about DC, we really haven't been discussing the magnetic fields that happen around wires. And the reason why is because in a magnetic field really only has a problem when it's changing. It's this changing of a magnetic field that causes issues. Remember, we go back to how do we create electricity? We have to have a change or something has to cut the lines of flux. If we just take a wire and just stick it right down in the middle of two very strong magnets, nothing's going to happen because you're not cutting those magnetic lines of flux. So we're looking for movement. Once you get movement, you have an issue. So movement can be two stationary magnets with the conductor going through those stationary magnets, or what if we had a conductor holding still, but the magnets rotated? Well, that wouldn't work with one thing going around. It'd be like, no, it doesn't work. But if we had took the magnets and went up and down, right?
Yeah.
Okay, same thing. So whenever you have this magnetic lines of flux changing, then you have issues, good or bad. And so with direct current, what happens when you connect your battery, electrons are going to flow through the wire, a magnetic field builds up, and it's just there. It doesn't change. So you don't have to worry about it. But now when we're talking about AC, it's constantly building up and going down, building up, going down. So now we have this electromagnetic force within every single wire that is constantly moving back and forth. Put another wire next to it, and now you're going to affect that wire because you have a magnetic field that's collapsing and growing next to a wire that is getting a magnetic field cutting across it. So this creates a whole series of problems or something to work with. So that is magnetic field in a wire. In a wire. Let's see, in a current with no voltage, I think that should be circuit. In a circuit with no voltage, free electrons randomly move around. Each electron has a magnetic field, but the randomness cancels out each other. Boy, that's a lot to write. All right. So in a circuit with no voltage, free electrons randomly move about, kind of like a 309 student, randomly move about. Right. Each electron has a magnetic field, but the randomness cancels each other out. When current flows, the electrons move in the same direction, and their combined effort creates a magnetic field. So when current flows, the electrons move in the same direction. And their combined effort creates a magnetic field.
Is this why you use shielded wire?
No, not really. That's more for radio things. Come on, where was it? Creates a magnetic field. Creates a magnetic field. And of course, this magnetic field extends outside of the conductor or the wire. So this magnetic field or magnetic force, field or force, extends outside the conductor. As voltage is increased, current is increased. You might have heard that before. And the magnetic force is increased. So as voltage is increased, current is increased. Current is increased. And the magnetic force is increased. And we already talked about this one, the left-hand rule of thumb. But it's a little bit different. And that's why I don't like to get into them very much. I don't test you on it because there's the left-hand rule of thumb, then there's the left-hand rule of thumb, and it's like, okay, how many left-hand rule of thumbs are there? Oh, there's all kinds of them. So it's like, which one are you talking about? So wrap left hand around a conductor It's nice that you guys are writing all this down. I'm surprised you just don't just print the notes off, off the internet. I'm just kidding. They're not there. It's like, what? Nope. Well, that's why I'm doing it. Wrap left hand around a conductor with thumb pointing, in direction of current flow, and your fingers will show the direction of the magnetic field. Fingers show direction of magnetic field. So conductor, left hand, negative to positive. I'm looking at it like that. Your fingers are going to show that the electrons are going to flow. The magnetic field will flow around this way. So what does that get you? If you're going to engineer something, you have to know which way the lines of flux are going to go in accordance with the next wire to figure out which way it's going to induce voltage in that wire. But for our practical purposes, all you have to know is that you have lines of flux cutting a wire, and you're pretty much good with that. Otherwise, it's going to get like, wow, okay, the electrons go this way, then they're going to, the field goes this way, then the wire is going to go this way, then they're going to cut it this way, so you're going to do the other left-hand rule of thumb to figure out which way. And by then, you would just want to say, never mind, I'm just going to go take some lawnmower repair classes and be done with this. Okay, so what does all this mean? Why do we care that these wires have this magnetic field that is growing and shrinking and growing and shrinking? Again, because DC, it does grow and it does shrink, but it only does it twice. What is it in DC? When does it grow? When you connect it. When does it shrink? When you connect it. Done. So it's only twice. Once when you turn it on, once when you turn it off. Other than that, who cares? So, but now we have this thing we have to talk about, which is induced EMF. Am I boring you? I'm sorry. I'll try and talk a little faster. Induced EMF. What does EMF stand for? I think you said electromotive force. I don't know. All right. So as we talked about, mostly me, talked about with a generator. A generator, a wire moving through a magnetic field through magnetic field will produce voltage. Will produce voltage. Or EMF, if you like. So with DC, direct current, the voltage goes from 0 volts to max instantly. That is, as long as current flows. So and then when voltage reaches max, the counter EMF stops. Well, wait a minute. Now I just threw in counter EMF. Max. The counter EMF stops. Well, now I got to talk about that one. I didn't put this in here. Okay, so counter EMF. So here's the funny thing. And this is really going to come into play with a lot of things. So kind of from this point out in the entire class, we're going to talk about coils. So it's really what we're into now, coils and magnetic influences on coils. Everything from here on out. So get used to it. It's one of those things like, I think I'm just going to skip learning about coils and EMF right now. It sounds confusing. I'm sure it'll be fine. Not from this point forward. This is all we could. In fact, starting next year, you guys, I think, are the absolute last Aero 302, 303 class ever. It will no longer exist after this. And you're thinking, damn it, I should have waited. It'll be called AMT 301, 302, and it's only 4 weeks long. Then you have AMT 303 and 304, which are 4 weeks long. This would be day 2 in that class. Same subject.
So that just helps you if you fail, basically.
Yes. So it's
Instead of retaking the 8 weeks,
you need 4 weeks. Yeah.
I should have waited.
So anyway, so I say this to say we're going to talk a lot about coils. And so one of the things about this whole process that we're talking about is this idea of counter EMF. And so when you're talking about coils and such, and which is just a wire that's twisted in a coil, we have a thing called counter EMF. So as the voltage surges into the coil in like a straight DC wire, it just builds up and it doesn't care. Now you coil that, and what happens is the voltage goes through. We have the left-hand rule of thumb, and so that voltage going through the wire building up causes an electromagnetic force about the wire, yes? Okay, so if we followed it very carefully, which I'm not going to do, in this left-hand rule of thumb and which way the north to south is going and how the other wire influences, I will just tell you that what happens is that magnetic influence tries to stop everything coming in, right? So electrons start rushing in, and the first thing that happens is, nope, we're here first, you stay out. Right? Reminds me of this country. So we're here first. So that's what happens. So that's called counter EMF. It wants to stop it. As opposed to, what if it worked the other way around? Then you'd have runaway voltage. Well, that would actually be kind of nice, but we don't get that. You know, it's like if one comes in, it tries to drag everything with it, and it's just a runaway, and so you have to be careful. If you added a coil, that'll go from 110 to 1 billion volts in a few seconds. You go, whoa! Okay, so, but it goes the other way around. As it builds up, counter EMF tries to stop it. Now, the funny thing is about AC, what happens is because it's always going back and forth, right? So we just got to say the electrons are coming from that way, going this way, hits a coil, goes, whoa, everybody stop. And then it slowly builds up and peaks out, and then it goes the other way. So now everybody stop this way. So it's constantly pushing back whichever way the electrons want to go. What does that sound like? Trying to resist?
Creating its own resistance?
It's creating its own resistance. But take an ohm meter and put across it. What are you going to get? That's fine, doesn't it? Throw it in an AC circuit. Now you've got this resistance that has been built up in it, but only in an AC circuit. We'll get more into that in a minute. You got a question?
That was being
Huh.
over. I was going to ask
Where was I? Let's see. Induced EMF. Okay. Voltage. Okay. When voltage. Okay. That's done. I'm done.
Thank you, Larry.
Okay. With AC, the voltage is constantly changing, which builds and collapses a magnetic field around the wire. This creates an EMF that counters the flow of electrons. You want me to write that?
Yeah.
You got a test on Friday. I'll write as much as you want. So, I remember to spell with completely incorrectly right there. So, with AC, the voltage. Problem is, I'm always thinking about the next thing I'm going to say while I'm writing what I'm saying, so sometimes it comes out what I'm thinking on the fence. It doesn't work. It is constantly changing direction, obviously, and amplitude. Constantly changing, which builds and collapses. Somebody's got their phone going off. We have a special project. A magnetic field around the wire. Magnetic field around the wire. Important point, this creates an EMF that counters the flow of electrons, that counters the flow of electrons. This leads us to the, that was your clue, Hannah. This leads us to the, oh, I thought I could count on you for this one. The so what?
Oh, yeah.
Lenz's law.
You didn't use the right tone.
How's the tone go? Give it to me.
And this leads us to.
I thought I did
So
that.
what? No, it's different.
Okay. Clearly it is. It didn't wake her up. Lenz's law. What is Lenz? Mr. Lenz. Maybe it's Mrs. Lenz. I don't know. Probably it's named after Mr. Lenz, but I bet you anything Mrs. Lenz told him about it, and he got the credit for it, because I know how that works. I always tease my wife about she's on her like 6th degree or something, because, yeah.
What?
Well, she helped my son with his bachelor's, and she helped me with my associates, then my bachelor's, then my master's. Now, Kate, so it's like she's got like 6 degrees because she's always involved. Lenz's law: a change in current produces an EMF whose direction is such that it opposes the change in current.
What?
What I just said. It's so simple.
I heard every word.
A change in current. Where do we find a change in current? AC. It's constantly changing, back and forth, back and forth. Sometimes I'll say, or if somebody else, anybody, it's alternating current. We'll say the voltage is going up and down, but what else is happening? The current's also going up and down. So don't let that fool you. It's the voltage goes up and down, the current goes up and down. So a change in current produces an EMF, electromotive force, whose direction is such that it opposes the change in current.
Makes perfect sense.
So to say it again, and I said it before, say it again. So what's happening is this current is coming in. That is a change of current. It is building up. It's a change. That change stops the change from happening. It's going to happen, but it delays it. So as the voltage comes in and the current starts to flow, you get the current flow coming in. It's changing. and it creates an electromagnetic force around the wires that are curled up, so that this wire that is curled next to this wire is affecting that wire. This one's affecting that wire. And so it's creating this magnetic force, and the magnetic force says, hey, electrons, stop coming in. But of course they're going to come in anyway. It just tries to stop them. And then pretty much you get to the peak, and as you go through the peak, and you have to remember when you're thinking about these waves, think about change. Where do we see the change? So between here, if we look between this time period and this time period, how much change do I have? A lot. It goes from here all the way to here. But from this period to this period, how much change do I have? Not so much. Right? So and then you come over here, we've got a lot more change because it's not very nicely drawn. But from here to here, you have a tremendous amount of change. And so when we look at these waveforms, we're going to talk about this later, especially in magnetos, where it's the period of time where you get the greatest amount of change. So not much happens here on the peak, so everything kind of calms down. And then it turns around and starts to go the other way. And what happens? The coil says, no, don't go the other way. Please, we just got here. Everybody stay. Come on, it's a party. Right? So everybody leaves and then tries not to leave, tries to hold it back. Okay, nobody go. So, all right. Got this written down? Okay. All right. This following that, let me see, those points right there. So that was V, and this is like V, and I made that point. This is 1. I think this sounds like something I would have added, because I always like to think about, well, what if it's the opposite? Kind of help me remember it. If the EMF didn't do what it did, which is it opposes the current flow. So if the EMF, we'll put it this way, did not oppose current flow, and instead helped it, did not oppose, but helped it, we would have runaway current. If that makes sense. It's just something I kind of made up to try and help me to remember that, it's backwards. So to kind of reiterate this, when current is increasing, the EMF does what? It opposes the increased current. So as current is building up, it says, stop it, don't build up, okay? But then we'll turn it around. When current is decreasing, it becomes a lonely old cat woman. Please don't go. Or cat man, I don't care. When current is decreasing, the EMF tries to keep the current, from decreasing. Keep current from decreasing. So hopefully you don't mind my personifying the actual electrons and current, because it's a little juvenile, but it works. The EMF, do you have a question?
I guess I'm just a little confused at what exactly the EMF wants.
What does it want?
Yes. So if it increases,
Fruits and vegetables mostly.
the EMF opposes it.
Uh-huh.
And if it decreases, they hold on to it.
No, it also opposes.
What?
As it's increasing, it tries to stop it from increasing.
Right.
When it starts to decrease, it tries to stop it from decreasing.
So it wants it to stay.
Not really. It doesn't really. No, I know what you're thinking. That's good thinking, actually. It kind of like it wants an equilibrium.
Uh-huh.
But I guess if it wanted anything, it wants no changes. You know, it's like me. No change is best. Just this. We just keep everything the same here, okay?
It wants DC.
The what?
It wants
It wants
DC.
It wants DC.
No change.
Right. The EMF. I'll put this, or sometimes called counter EMF, which I think is more appropriate if it's actually fighting something. Counter EMF, which can also be called CEMF, counter EMF, which is counter EMF, is 180 degrees out of phase with applied voltage. We'll kind of come back around to that one. So I'm okay if you don't quite grasp that one. I think it's going to be fine. So, all right, let's do VI. All right, the amount of, we'll call it self-induced EMF, big EMF is dependent and proportional on three things. And those three things are, one, okay, talking about AC, frequency. So more changes equals more EMF. So if I only had one cycle per minute, and it took an entire minute for it to build up and drop down and come around, that's not much change at all, right? It's, shoot, at that point, it's practically DC. It's not, but you have very little change. But now really increase that frequency, you know, 400 hertz, 400 cycles per second. I mean, that is just going crazy, back, forth, back, forth, back, forth. That is really going to drive this thing nuts, so to speak. So more frequency is going to be more EMF. Current flow. If you only have a little bit of current flow, you only have a little bit of effect. So more current equals more EMF. More EMF. And 3, the physical shape of the conductor. Physical shape of the conductor. I should say of the coil, really. We'll call it conductor because we just talked about inductor. In a straight conductor, counter EMF, CEMF, the thing that opposes the current flow coming in. I wrote in my notes, a straight conductor CMF is determined by the lines of flux. Well, I'm just going to say is limited. Because it's straight. It doesn't cut across any other coils or any other conductors. So it's really just kind of, it will affect what's next to it, its neighbor, but that's another circuit half the time. So you're having to say it's negligible. So it's limited. It's really dependent upon the lines of the flux it's cutting across, which really aren't even there. So not such a big deal. But if the conductor is coiled, well, what do we get? We get a coil. So the EMF produced in this same wire cuts through other wires. At multiple points. Okay, this significantly increases EMF, So this, yeah,
What do you mean by cuts through other wires?
cuts through. So when we had the drawing yesterday of the generator and the armature was going through those lines of flux, it's cutting through is what we say. What was I going to say? 1, 2. Oh, this, not this. This significantly increases CEMF. Means it really wants to stop it. Straight wire is almost negligible. Is almost negligible. And coiled wires, not so much. I don't need to write that. Yeah? Huh? Negligible. Not so much. Very little. Very little.
Does the way you coil the wire matter? Like, clockwise or counterclockwise, that kind of thing?
I believe it has to.
So I'm trying to imagine. How
I know. I know. In my mind, it always does have an effect, but yet, it not necessarily. Because you wouldn't. It's AC. It goes back and forth.
Yeah.
So if you coil it one way, just in a minute, it's going to seem like it was coiled the other way anyway. So. All right, so let's talk about these coils, or another word for a coil is an inductor. Inductor, or a coil. Yeah. All right, so an inductor. Inductance is defined as that property of an electrical circuit that tends to oppose any change of current through the circuit. That sounds like what we've been talking about, really. It's just kind of a repeat. So inductance. Inductance is defined as that property of an electrical circuit, of an electrical circuit that tends to oppose any change of current through the circuit. So inductors are all kinds of different, and they have different properties and different things they do. And I know it's almost break time, so we'll finish this point. So a coil or an inductor, but a coil of wire, we'll say may or may not be wound around a core. Wound around a core. Like I built this little thing right here. Well, that's a coil. It's an inductor. Is it wound around a core? No, it's wound around plastic with a magnet inside. So no core, coreless. But the core has a big effect on what happens within this coil of wire. So core may be magnetic material. We're going to see that a lot coming up, which increases, which that didn't work out well, which increases inductance, meaning the opposition, and also magnetizes the core. So in other words, if I would have if I take this magnet out and I put a piece of soft iron inside here and run some current through here, then the bar that's going through here, I'll make an electromagnet and it will magnetize that piece of steel that's going through there, the soft iron core. You don't have to have a soft iron core, or you can change it. So core may be non-magnetic. Air, some other type of insulator. And if you do that, it decreases the inductance. All right, that brings us up to break time.